Hi, welcome to part 2 of this video playlist about the best methods for preparing alkyl iodides from aliphatic alcohols. This presentation is about the use of compounds containing phosphorus-iodine bonds as deoxyiodinating reagents. The most common laboratory reagents for preparing alkyl iodides from alcohols are mixtures of triphenylphosphine with iodine or with another electrophilic iodinating reagent. Alcohols can, however, also be converted into alkyl iodides with mixtures of elemental phosphorus and iodine, which react to yield phosphorus triiodide. These reactions are closely related to the Mitsunobu reaction. From the alcohol and the phosphorus iodide, a pentavalent alkoxyphosphorus derivative is formed, which decomposes by intramolecular nucleophilic substitution to the alkyl iodide and some derivative of phosphorose or phosphoric acid. Depending on the electrophilic iodinating reagent chosen, the reaction mixture will turn more or less acidic. According to this mechanism, only anionic, phosphorus-bound nucleophiles can compete with iodide, but not neutral nucleophiles such as pyridine, imidazole or amines. The latter may, however, react with the alkyl iodide if the reaction temperature is too high. This reaction is often performed in the presence of one equivalent of imidazole as a weak base, because this seems to increase the yield of alkyl iodide. This base, however, is not strictly required unless the alcohol is acid-sensitive. Suitable iodinating reagents include elemental iodine, N-iodoimides, triiodoimidazole, and carbon tetraiodide. As a low-cost alternative to triphenylphosphine, triphenylphosphite can also be used in this reaction, but alkoxybenzenes may result as byproducts. Deoxyiodinations with phosphorus iodides usually proceed with clean inversion of configuration. The most important advantages of this strategy are the mild reaction conditions and the high yields, what makes this particularly suitable for expensive alcohols. Furthermore, no large excess of iodide is required, and because of its responsiveness to steric effects, selective monoiodinations of polyols can be achieved. Main disadvantages are the high cost of the phosphine and the difficulty of removing the resulting phosphine oxides from the product. Furthermore, large amounts of phosphorus-containing waste can be difficult to dispose of. This example is the preparation of methyl iodide from methanol. Because methanol doesn't cost much, an excess of the alcohol was used to enhance the yield with respect to the iodine used, which is the most expensive reagent in this synthesis. In this example, a higher boiling primary alcohol was converted into the corresponding iodide. Interestingly, only half an equivalent of iodine was sufficient to attain a high yield of product, what means that both iodine atoms were used, the second one probably by the same mechanism as in hydrogen iodide-mediated deoxyiodinations. No large excess of phosphorus was required, making this a very affordable strategy for the preparation of alkyl iodides. This example is the conversion of bok-serine methyl ester into the iodide, which illustrates the mildness of this strategy. Upon activation, serine derivatives often undergo beta elimination, but this did not occur here, and a high yield of the desired iodide was obtained. A chromatographic purification was, however, required to remove the phosphine oxide. In this example, a secondary unreactive alcohol was converted into the iodide by treatment with triphenylphosphite and N-iodosuccinimide without the use of imidazole or other bases. Despite the low reactivity of the starting alcohol, still a substantial amount of the iodide was obtained. Unfortunately, the authors did not disclose what happened to the remainder of the starting material. When using triaryl phosphites instead of phosphines or elemental phosphorus, one potential byproduct is the aryl ether. Alkyl phosphites cannot be used because the phosphite alkyl groups would also be converted into alkyl iodides. As shown in this example, the combination of triphenylphosphine and iodine enables the selective deoxyiodination of primary hydroxyl groups in the presence of secondary hydroxyl groups. Interestingly, the unreactive hydroxyl groups did not consume any phosphine. In this instance, the use of a weak base such as imidazole made sense because the starting alcohol was an acid-sensitive acetal. Carbohydrate-derived acetals are more resistant toward acid-catalyzed transformations than other acetals, but it is always a good idea to try to avoid potential problems. So, what can go wrong? Besides iodide-mediated reductions, one typical side reaction of deoxyiodinations is elimination to form olefins. Some phosphorus-based deoxyiodinating reagents, such as methyl triphenoxyphosphonium iodide, are in fact used for the dehydration of alcohols to prepare alkenes. Bases generally favor the formation of olefins, while acidic conditions and an excess of iodide will promote the formation of alkyl iodides. In the examples on this slide, no base was used, but still the tertiary hydroxyl groups underwent complete elimination. In this example, a secondary unreactive alcohol was converted into the iodide with inversion of configuration. As byproduct, an arene was formed by elimination of the hydroxyl group and an alkoxy group. High reaction temperatures often promote elimination reactions and may have contributed here to the observed arene formation. Inherently unstable alkyl iodides, such as the product of this reaction, will of course be difficult to prepare in high yield. Alcohols and alkyl halides with electron withdrawing groups in beta position readily undergo elimination, and olefin formation was probably the main reason for the low yield of this reaction. If 1,2-diols are treated with an excess of deoxyiodinating reagent, olefins will often result because 1,2-diiodoalkanes are unstable and decompose into an olefin and elemental iodine. Unlike the other halogens, iodine does not add to olefins to yield diiodoalkanes because these are too strained and unstable. The reaction on this slide is an example of such a reductive deoxygenation of a 1,2-diol. Only a small amount of iodoalcohol was obtained, formed with retention of configuration. The stereochemical outcome suggests some enchimeric assistance by the pyrimidinone group. If mixtures of phosphorus and iodine are used without any additional base, the reaction mixture may turn strongly acidic due to the formation of phosphorose or phosphoric acid and small amounts of hydrogen iodide. This may cause rearrangement of acid-sensitive alcohols. Acidification can be prevented by adding a base, but not a large excess, because alkyl iodides readily undergo elimination or substitution in the presence of bases. Phosphorus iodides are reducing agents, and during the reaction, other strongly reducing intermediates may be formed. Thus, similar as in reactions with hydrogen iodide, the reduction of various functional groups can occur. In particular, sulfuric and sulfonic acid derivatives, amine oxides, or pyridine N oxides can be reduced and are usually incompatible with these reagents. The reaction on this slide shows the many products formed from cinnamyl alcohol and iodine and hypophosphoric acid. Here are some more examples to give you an idea of the scope of this reaction. The reagents described by now, namely hydrogen iodide and phosphorus iodides, enable the economic preparation of iodides from a wide variety of alcohols. Some additional reagents have been described though, which are less versatile, but may offer some advantages in special situations. These will be discussed in the next presentation. See you there.